And welcome. In this video, we're going to take a look at an example of computing type 1 and type 2 errors. And I just want to motivate the idea of why we studied probability first before we really get into the statistics portion of talking about confidence intervals and hypothesis testing and, getting inferences on population parameters, is because if we want to do a study like this, we have to compute our type 1 and type 2 errors. That requires us to know things about probability. And, it could be a binomial probability that we're computing. It all depends on the, what your population is following. It could be a normal distribution probability that you're computing. So let's take a look at what we're going to do in this example. The proportion of adults living in a small town who are college graduates is estimated to be 0.4. Okay. To test this hypothesis, a random sample of 100 adults is selected. If the number of college graduates is anywhere between 30 and 50 inclusive, we fail to reject the null hypothesis. Otherwise, we shall conclude that P is not equal to 0.4. So you're looking at a null hypothesis here that P is 0.4 versus the alternative hypothesis that P is not 0.4. And we're not actually going to run the hypothesis test here. We're going to compute the type 1 and type 2 errors. So A, evaluate alpha, assuming that P is equal to 0.4, right? Alpha is the type 1 error. So let's take a look at alpha. Remember from the previous video that is the probability of a type 1 error. And what is a type 1 error, right? That's the probability that you reject the null when it is true. It's making a mistake when the null hypothesis is true. So what's the probability that we reject the null when it is actually true? When it is actually true. So let's take a look at this. What are we given here? We are given range between 30 and 50 inclusive. We fail to reject when it's inside of that. So when do we reject the null hypothesis? We reject it outside of the 30 to 50 window. So we could be less than 30. Since we're talking about people here, this is a discrete random variable, less than or equal to 29. Or greater than 50. And again, because we're talking about the number of people here, greater than 50 is the same thing as being greater than or equal to 51. All right. These are binomial probabilities. If I had this in a table with a probability of 0.4, I could look this up in the binomial sums table for 29 and a probability of 0.4. N goes up to 100 though, and so we're going to have a hard time figuring this out using our table when N goes up to 100, because in that case we'd need probability 0.4, and we're going to need 100, and then we need to subtract below 50. And I'm pretty sure that the table in the back of our book here does not have that. Let me just do a quick glance here. Poisson probabilities, binomial sums. Yeah, only goes up to N equals 20. So we're not even close to getting that done. Only goes up to N equals 20. So we would not be able to use our table to do this. So how can we get around that? We can definitely use the normal approximation here. We can definitely use a normal approximation, right? X is approximately normal. We can approximate the binomial random variable with a normal random variable. Can approximate binomial with normal distribution. Normal distribution. Recall that the mean is n times p. Mu is equal to n times p. So n here is equal to 100, right? Because we have 100 adults in the sample. And for part A, we are assuming that the null hypothesis is true. So in that case, we're assuming the true proportion of success is 0.4. N times p then is 40. And variance, sigma squared, npq, or np times 1 minus p, would be 100 times 0.4 times 0.6. That would be 24. That would be 24. All right. And again, this is a binomial random variable. This is discrete, so we need to employ the continuity correction. Let's not forget our continuity correction here. So let's see how we can do this. This should be equal to the probability that x is less than or equal to 29. We'll convert to the standard normal distribution here. First, we're going to have the continuity correction, which is the 29.5. Don't forget that. Continuity correction. We're going to add a half. No, less than case. Continuity correction. Right there. And then converting to standard normal, subtract the mean, which is 40, divided by the standard deviation, which is the square root of 24. Plus probability then. In the greater than case, your continuity correction is slightly lower than 51, so we're going to include anything up to, or anything starting at 50.5. 50.5, 50.6, right? All of those values would round up to 51. So our continuity correction here is at 50.5. Continuity correction right there. Squeeze my arrows in. And then subtract the mean. Divided by the standard deviation. All right, so let's go ahead and take a look at these values. This is the probability that z then is less than or equal to, carefully running those through a calculator, I've got about negative 2.143. And then this is actually the same thing, same difference in the numerator, it's just the positive version. This is positive 2.143. Okay. And that's actually a nice thing to notice, because if you think about this, these are symmetric issues, right? In the sense that less than the negative, if I draw a normal distribution curve, and I say here's my mean mu, and if I'm at negative 2.143, right there, and I want this area, but I also want the area bigger than the positive, those are the same areas. Those are the same areas. And so this is going to be equal to, twice. I only need to look one of these up in the table. Twice the probability that z is less than or equal to negative 2.143. Twice that probability. Okay. And we can go look this up in the z table. We're not going to have the 1.143. We're going to have to choose between 0.14 or 0.15. This is pretty close to 0.14. And so if I take a look at the value at negative 2.14, that probability is 0.0162. 0.0162. We double that. Times 2. That's 0.0324. There's our alpha, or our level of significance. 3.24%, approximately. Again, we have a little bit of approximation when we're looking up in the z table there, kind of splitting the values in between. 0.032, though, should be pretty consistent. There's alpha, our type 1 error. That's the probability that we reject the null when it is true. That's a pretty low probability, right? 3%, that's a pretty low probability. That looks good. How about B? Evaluate beta for the alternative, where P is equal to 0.3. Let's take a look at part B here. Part B, I should say B, not beta. Part B. We want to find beta. Beta is the probability of committing a type 2 error, right? Now, what is the type 2 error? That's the other kind of error. That's making a mistake when the null hypothesis is actually false, right? This is the probability that we fail to reject it when we should. We fail to reject the null when, in fact, it is false. And in this case, we're taking it for the false case that it is actually 0.3. P is equal to 0.3. Fail to reject the null when the true probability of success is 0.3. So what region of x values do we fail to reject the null? We fail to reject the null if the number of college graduates that are between 30 and 50 inclusive. 30 and 50 inclusive. So 30 and 50 inclusive. This is our fail to reject region, right? Fail to reject region. Again, we can do a normal approximation here. We can use the normal approximation. We have n equals 100 again, but be careful. You're not going to use the same normal approximation we did in A because we're assuming now that P is different. We're assuming that P is actually equal to 0.3. So we can say that X is approximately normal with a mean of, this time, 30, a mean of 30, and a variance of, what is the variance here? NPQ, 100 times 0.3 is 30, times 0.7 is 21. A variance of 21. So, and again employing a continuity correction, the probability here is approximately equal to, what's the continuity correction? Again, on the greater than component of this, we want to be slightly below 30. We want to go slightly below 30 and slightly above 50 to add for those round offs. So that would be 29.5 with the continuity correction. And subtract the mean, which is 30 here, divided by the standard deviation, square root of 21. And the continuity correction on the upper side of things would be plus 0.5, so 50.5 minus 30 over the square root of 21, right? 50.5. Continuity correction there and there. 50.5. So, just got to run those numbers through here. Notice this time it is not symmetric. 29.5 minus 30 divided by the square root of 21 is negative 0.109. So it's pretty close to negative 0.11, which is probably what we'll look up in the table. And on the right, the upper bound here, 50.5 minus 30, that's 20.5 divided by root 21, which is about 4.47. 4.47. So now we have this normal probability. I want to take the probability that z is less than or equal to 4.47. We get everything we want minus the probability we don't want. That would be less than negative 0.109. And this value right here, 4.47, that is so many standard deviations away that it's approximately 1, right? You're not going to find that in our table. Our table is capped off at about 3.99. So, and when it's at 3.99, the probability is 0.999. So this is essentially equal to 1. And then we can look this up in the table. Probability z is less than negative 0.109. I've got about 0.4562 for that value there. And so 1 minus that is about 0.5438. 0.5438. Okay. So that is the probability of type 2 error. 54%. That's a pretty big value. Part C is asking us, is this test a good procedure? Is this test a good procedure? And I would say, generally speaking, no, not really. A good procedure is pretty vague, but not really. While the type 1 error is small, alpha is small, right? Alpha is very small. Alpha is about 3%, right? This is less than 5%. Alpha is small. The beta, the probability of getting a type 2 error, beta, which is about 54%, is very large. Is very large, right? The power of the test is 1 minus beta. The power of the test is 45%, right? A power of 45%. Approximately 45%, right? What does the power tell us? That's the probability of making the correct choice when the null is false. Probability of making the correct decision when the null is false. You would want to make the correct choice more than 45% when the null is false, right? Beta equals 54% is very large. So generally speaking, is this a good procedure? I would say no. Lean towards the not really idea, okay? How could we change that? How could we change that? Is we would have to change our fail to reject region, right? If we narrow the fail to reject region, if we narrow that, we're going to increase the type 1 error a little bit, but we'd also decrease the value for beta as well. But that's neither here nor there. This is how we can compute our type 1 and type 2 errors.